Good afternoon to you, all of you, Bhutala.
Good afternoon, sir.
Yeah,
Good
today,
afternoon, sir.
good afternoon. Today, 15th January 2022, lesson number 5, and welcome to Thermodynamics subject. All the three groups, manufacturing, mechatronics, and BST. Semester 2, B2 students. So, we are going to learn something interesting, but if we plan today, again, it's about understanding. We have to learn about steam and gas expansions. We have to learn about work done, heat and work, and the first law of thermodynamics. So this is what I have outlined today. But before starting any of this, so let me start something, a simple mechanics example. Okay, simple mechanics out of thermodynamics, out of thermodynamics. Out of thermodynamics. Let's say, listen from dynamics. Dynamics. So if you think of a mass, let's say mass M. It's a mass. M. And a force is being applied. So let's say this. On the mass. So let's say the resultant force. The resultant force. And let's say it's on this direction. This is the resultant force. And generally, the force you denote by F. Okay, you denote by F. So F. The force on the mass, the resultant force. So when the resultant force is F in this direction, and let's say the mass also moves on the same direction. Okay, on the same direction, and let's say a displacement because of this force applied. Because of this force applied, this may take a little time, but displaced. So let's say this is the displacement. It's a vector again. Yes. And this displacement, let's say X. Or even let's say D is the displacement. Yes. Yes. Now imagine this force F applied on mass M. Something happened to this mass. Something happened means the the dynamic state, the state of this mass changed. Means it moves. You see the mass is moving. So what happens to this F? F is the work or the force, resultant force on mass. So continuously putting this force on the mass. So don't you feel that because of F, mass received something because of F? Because it's applied on the mass M. So because of F, mass received something. Okay, mass received something, and as a result, even this moved. So I will write a word here. Work done. Do you see this? No. But the mass feel this. On the mass. Work done. So you have to not to say imagine, but practically you can experience this. Force applied, the resultant force applied on M. What happens is this F acts on M and M displaced, because of F. So work done on the mass. So you should not memorize, but you should feel this mystery. මේවා නිකන් අර සුබාදහමේ රහස් වගේ පුතා, mysteries. Yeah, you apply the force. Imagine there is something like a force. Even you can apply force on a mass. සමහරලාට වාහනයක් කීම තල්ලු කරුවොත් you are applying a force. Even you are capable of applying a force. Yeah, so it's a capability even we are having. So work done, we would say this work done we can quantify as force times displacement. Okay, that is reasonable because the longer displacement work done, that work done is more than work applied for a shorter displacement. So work done, force times displacement is quite reasonable. And this is considered as a definition somehow for this F times D as the work done. Okay, this for a linear force. So this is for the linear force. For a torque, okay, means turning effort. So this one, you may notice that torque is the turning effort times angular displacement. It's reasonable. Okay, it's very reasonable definition. So turning effort times angular displacement. Turning effort we call torque. Okay, it's a different story. So what I want to say is, even engine, your motor bicycle engine, car engine, okay, or even when you pedal the bicycle, the torque is applied. So this is a linear, and this is again a work done. Okay. Actually, because of the work done, what happens? Because of the work done, what happens? The energy level of this mass changed. Because of the work done, energy level of the mass changed. The nature is like that. So energy level of the mass means the mass energy change. So that is equal to, here for dynamics, kinetic energy increase. Kinetic energy increase. Even for this, kinetic energy increase. Okay. Kinetic energy increase. So you know this. Okay. Kinetic energy means you can see kinetic energy increase, but you can see this is something related to the velocity, the rate of this change of the displacement. So this kinetic energy is something related to something related to velocity or the movement of the mass or the motion of the mass. Motion of the mass. So same way for this turning effort, also there could be turning mass. Again, it's for the rotational motion of the mass when you apply a torque. So two things here. Work done. Something related to motion of the mass. And C, kinetic energy. Okay. Kinetic energy. Now, let's say for the gas molecules. So gas molecules, again, tiny masses, the same M applicable. So you can see here, the gas molecules are continuously in motion. Okay. Hit the walls, bouncing back, collides with the other molecules. and this is in continuous motion. Imagine, how can you apply a force on this? How can you apply a force on this? Example, here, in the big mass M, you apply the force. So the same way, there can be a way of applying force on this. Interesting, eh? Interesting. So if you apply the force, or we would say, instead of applying the force, energizing. That's the best word. How to energize these molecules? So back to the previous. So here, you are energizing this mass by applying the force. You are energizing. So the velocity change. Here, there is a velocity, because change in kinetic energy. So we have a velocity. Let's say V1. V1 here. And because of the force, this mass is energized. Now moving very fast. V2. This energizing. So how can you imagine to have a similar effect? Interesting, you know. Interesting. Interesting. So energizing the molecules of gas molecules, energizing. The gas molecules. Energizing of the gas molecules. So once energized, you feel those molecules moves fast. Okay, those molecules move fast. Less energy, less velocities, high energy, high velocities. So for the gas molecules, when the velocities are higher, means higher kinetic energies, you may see higher temperature levels. So temperature is one way, a reflection of the level of energy in these molecules because of the motion. Okay, because of the motion. So related to kinetic energy. That's why if you want, let's say in the vegetables, so there are molecules. Okay, so if you cool the vegetables down when you put in the refrigerator, molecules become cooler, means reduce the molecular motions, reduce the molecular activities. So it preserves the freshness. Yeah. So energizing the molecules and also de-energizing or reducing the energy levels of the molecules. Both are important for the applications. Both are important for the nature to work. That is very important. Okay. So energizing. So Here, this molecule's energy level, we call it internal energy. In general, because of these molecular motions, the energy level we call internal energy. But here, for the masses, in the mechanics, this is, we directly call that's a kinetic energy, energy because of its motion. Okay, so that's why this is the energy, kinetic energy, but here, energy internal to this system, we call the internal energy. It's also a reflection of kinetic energy. So you can know the word internal energy, not necessary to go in a deeper understanding, but if you can have a general understanding that, yeah, internal energy is something internal to this system where the molecules, they have the kinetic energies, and those kinetic energy collective, let's say for 1 kg represents internal energy, kilojoule per kilogram of that much. So it is something like that. You should be familiar with the internal energy. So applying a force on a mass, kinetic energy increase means the mass is getting energized. So here, how the internal energy can be increased, how we can increase the internal energy. You know, your bicycle, you can energize somehow bicycle, you can let it speed. So the total kinetic energy, including you, yeah, the energy level rise. Of course, engine helps so that derive the power for that, and the vehicle or the bicycle moves, and you and the bicycle, the dynamic system is getting more and more energy, and you can see you are being accelerated with the bicycle. Okay, you are getting energized dynamically. So here, how to make these particles, these molecules become energized more? How to make it energized? Yes. So that is our approach today before we are going for the laws. Yeah. So how to energize? So that's the part. How to energize? The gaseous molecules entity, the gas molecule entity. How to energize? How to make them move fast? How to energize? That's the point. Okay. So one way of energizing is you can heat this up, add heat up this. So heat addition. So you can understand now very well. All you can realize this. Heat addition. These are nature's phenomena. Okay. So you should understand this, and you are not going to memorize this. Heat addition. So what is heat? Some more issues. Huh? But you know that when you apply heat to water, water boils. Boils means raising of the kinetic energy levels of the molecules. Molecules are violent. Movements are quite violent. And later even go into the steam phase or the gaseous phase. So heat addition is one way. Okay. When heat is added, gaseous molecule or the gas molecule entity or the container becomes, this gas become energized. That's why even this pressurized containers, you are keeping the pressurized container in cooler places, because if you put it in a warmer place, the gas molecules in the container, the pressurized container become more energized, and even that can be exploded. Example, the cooking gas cylinders. So you have to keep it under a shade in a cooler place. And that LP gas cylinder, let's say, should not be exposed to direct sunlight or direct fire or in a warmer place. So that is for the safety, because if not, further heating means more energizing can make the cylinder rupture and the gas will come out in violent ways. Okay. So heat addition is one way. You can energize the gas. So let's say this is Q. So you're adding Q amount of energy as heat. So once you apply heat, same like you apply force on mass. So apply force on mass, mass energized. So apply heat on the inside, so the molecules somehow receive it. Molecules receive it, not the space, but the molecules in the space. When the molecules receive this heat, what happens? The energy level goes up. Okay, the energy level goes up. Okay, so what happens is, because of this, let's say energy, internal energy of the gas entity or molecule entity. Okay, before applying Q, before applying or before receiving, because molecules, they are receiving, we are applying, but we have to think like molecules. Before receiving the heat Q, let's say this is U1 or E1. Okay, or E1, both are okay. And then after receiving, what happens? After receiving, just before and after. So after receiving Q, let's say U2 or E2. then surely you can say that U2 is now becoming U1 plus Q. Okay, U2 is U1 plus Q. That is quite obvious to you. Or even you can say E2 is E1 plus Q. And receiving heat to the system, we consider this side is the positive way of heat transfer. Positive means receiving heat towards the system, okay, from the outside, from the surrounding. So U2 is U1 plus Q because originally U1, because of receiving Q, now becomes U2, that is U1 plus Q. Or E2 becomes E1 plus Q. Also, you can say that the rise or the increase we use the symbol delta. What increase? Increasing of U. The internal energy is U2 minus U1. Because now U2, previously U1, that is equal to Q. So Q is the rising of the internal energy. Or else in terms of delta, E. So E means energy. U is a standard form, standard notation for energy. Minus U1. So this is phenomenally like this. So same way, a mass, you apply force, increase the energy. Here, again mass, but molecular entity. See the different way of saying it, but a mass is there. But it's a collective of tiniest particles, molecular level ones, floating within the space, moving within the space. Not to say floating, moving within the space. It really occupies. So then, same like applying force, here you are applying heat and you are energizing this. Okay, you are energizing this. Interesting. Okay, interesting. Now let's say I will take the IC engine compression stroke. You know this. Let's say this is a diesel engine. So the piston. Let me take the piston here at this time. So compression stroke. So you have the gas entity here. That's the beginning. End of the compression stroke. As the piston moves, it comes like this. Let's say this is a diesel engine. You know, compression ignitions. CI engine. Okay. So compression ignition means auto igniting once the fuel comes in. So how is it possible from changing this air entity from here to here? See, you call it compressing. So how you are compressing? You have applied the force on the piston and the piston moves. Yes. So now it is interesting. Now you are applying a real force. If it's a force can be varying with time and displacement, but it's a real force. Even here. So where are this work done? What happens to this effect of the force? So here effect of the force in this single mass, big one name, goes into the mass. Okay, and the mass moves and the kinetic energy increase. Now here, this effort force. So there is a work done here. Work done on the gas molecules takes place here. Work done on the gas molecules. So gas molecules together receive this work done. Okay. So because of this force. So gas molecules. See, the dynamics example really helped you. Eh? Gas molecules together receive the work done. Okay, work done. So receive the work done. Because work done on the piston transfer the work done to the molecules. Okay, so gas molecules together receive the work done, but this is a work transfer because it's applied on the piston. Through the piston, the work transfer to the gas entity transfer. So in gas, we can see the heat and work transfer. Same here, heat addition. So from the outside, through the walls, maybe heat transfer here to inside. Okay. So heat addition, or this is the transfer. So that's why we can say heat and work transfer. So work transfer into the gas molecules means the entity means the thermodynamic system. Then where is this? You know, in compression, this diesel engines, when you compress, temperature goes very high. That's why when the fuel spray, atomized diesel droplets add into this, it can be a big further rising of the pressure, because further energizing of the molecules. So work transfer into the system. So what happens is the same way. Now internal energy of the entity before receiving the work. Let's say work W. Before receiving the work, W is U1. It's the same. So I just replace heat by work. Same like previous. Internal energy of the gas entity after receiving the work W is U2. C2. Okay. Then your energy balance comes here. The same now becomes W. This is the beauty you are seeing. Energizing can be done by adding heat or by adding work to gas. Very nice. Okay. So when you add work here, the system boundary, see one side is moving and the system boundary is changing here. So this is a moving system boundary. Even you can add the work with non-moving system boundary. Later we will look into that. But now you can say this. So combinedly, okay? if you are adding both heat and work to the system, if you're adding both heat and work, so your heat addition and the work addition. So work addition that one we call work done or transfer, W. Now, the same. U2 is U1 plus Q plus W. So delta U is, see W, we consider positive towards the system. Towards the system work done on the gas molecules in this enclosure. We consider this the positive direction. Work done, okay, on the system. So positive. Towards the system, it is positive. So towards the system, we consider positive. Means positive is really increasing. Positive, that's why this is increasing. So say Q plus W, addition of this. Now all together. So Q plus W plus W. Interesting. Okay. So for a closed system means no mass transfer between surrounding and the system. So you have 1, 2, 3, 4 expressions. So all the 4. So this is the expression we call the energy balance for a closed thermodynamic system. Okay, energy balance, because the energy, it won't lost. Also, there may not be additional somehow creation of energy. So the same energy, so addition of heat, equal amount of rising of internal energy. Addition of work, equal amount of rising of internal energy. So addition of both heat and work. So W plus Q amount of rising of internal energy. If you combine those. Okay. So this is the expression for energy balance or the first law. You can read the first law, it's in your notes. So this is the first law of thermodynamics, related expression for a closed system. Okay, so if the boundary is moving, definitely you have a work interaction, or even there can be other ways of work additions as well. Interesting. I believe you can understand this. Okay, it's interesting. Any questions? Yes, work done. We know little now. Heat we know a little. Work we know a little. Energy balance. For first law of thermodynamics, we know a little. Not complete, but we have some solid practical sense of this. Okay. For further understanding, you can go through your notes. One time note I passed to you. You can go through that. Okay. Give me a second, Putha. So this is jug kettle. Inside the kettle, there is a heat element. There's a heat element. So I'm going to add a heat element for that. Of course, heat element is there, but for our better understanding. Anyway, there is a heat element inside. And of course, water is there. Anyway, water is there. Let's say here got water as well. So now you can see the thermal energy is added from heater to water. That's how you are noticing. Thermal energy is being added. Yeah. Q. Let's say Q. Okay. So is this Q or W? Is this Q or W? Oh, this can be both. Can be considered Q or can be considered W. Heat over. Anyway, it's a kind of energy input. So electrical energy comes here. Electrical energy. this element, of course, we call heats up. And now there is a kind of energy transfer from the heat element to the water. You may hear a water heating noise even before water boiling. Can you hear when you on the jug kettle? Maybe after a minute, you can hear a noise. What is this noise? Actually, molecules are moving little more violently, more agitated. A kind of agitation. Agitation. So agitation means it's a W. Okay. Because of this agitation, we hear the noise, something like that. Boiling, of course, a higher noise. So more agitation. Okay. So kind of agitation. So this heater does this agitation very silently. So, and another way, you can see the water getting heated because temperature is rising. You feel hot. This is Q. But don't say different W and different Q. So you can consider this as either W or Q. Anything is okay. Okay, anything is okay. So your electrical energy comes here. Let's say 10 watts. Energy or power. Let's say energy. E1 or E here. So this E can be if you consider it is fully efficient, The heater is normally the energy transfer to. The same way is Q, or you can consider as W. Okay. So adding heat makes the molecules move. Molecules are masses. Makes the masses move means it's something like a work done, W. So electrical energy input of this nature, you can consider as a work addition or as heat addition as well. So this can be W or even can be Q. You'll understand? Okay. So can be both. Because from this example, you can see that. So heater, yes, energy, the conversion from electrical to thermal, but thermal finally can be something like a work done possible. So it is okay to think in that way. Or you can see direct thermal energy. So same as the internal energy rise. Rising internal energy, you can see, you can notice it even from the noise. It's getting energized. Move and move, more noise come. Okay. Yeah. So noise coming means it's a kind of energy loss, because noise come means that noise, because of part of this energy. So that energy loss from the system, if the noise is there. Okay, so for perfect, efficient heating, you should assure no noise till boiling. That's another interesting point. So noise. This noise is one way, and energy loss from the system, and hence for a good thermal heating system, this noise if kept to the minimum, would be a low entropy or energy saving process. Yes. So yeah, you feel noise is very good because it shows that it's really boiling. But anyway, I don't know whether my here what I wrote is okay or not, but noise is something energy transmitting out from the system. So it's a loss. But still we have to have energized water, but that energy should not come out. So noise going out. So noise. See if you design smooth silent one, you know it is better. So some cases, no, many cases, also the heat loss. When you touch the kettle surface, it's hot means heat loss. So these also should be minimal, noise and heat. Yeah, because for that you have to add extra energy input to this. So energy, noise, energy, heat loss. Okay, energy, heat loss. So noise loss. So I have to minimize all. Interesting. Okay, interesting. Any question? So now these slides may help you to understand the first law of thermodynamics for closed system. Okay. Or even energy balance. So now you can read your notes, not now. So there will be better understanding for you. Okay, refer your note. Good. Steam power. Old engines. We use coal, burn here, makes water, boil, then energized steam comes to this chamber. We call this engine, and moves the piston. Because of the flywheel effect, the piston can displace the de-energized steam out. Then energized steam comes in, de-energized goes out. So that's how, this is something like two-stroke. Power stroke is there. And then exhaust stroke is there. So mainly two you can see. A simple construction. So I have a question in mind for you. Before that, you notice this. When the steam lost energy after delivering or driving this, go to the exhaust, then the fresh energized steam comes, moves the piston, and turns the wheels. After lost energy, the de-energized steam exhaust. So not only the steam emission, but this burning of coal, other flue gas emissions also there. Two emissions. Okay, so the steams are not harmful to the environment, but this burnt coal emissions are not good for the environment. Again, it's like steam power. Steam in, push the piston. So power and exhaust. Maybe something like a schematic showing power generation. Okay. So steam has this power. Even in Noroccioli, there are steam power generations also maybe in combined cycle power plants. The last stage may be the steam power. So what's the phenomena associated with this power stroke? That is the question I'm asking. What's the phenomena associated with this power stroke? What makes the power delivered in this stroke? Energized teams, not that much. A little is enough because full of energy. Moves the piston. Piston turns the wheels. Even the wheels have the flywheel effect as well. You may be learning about flywheels in your mechanics maybe. Because of the flywheel effect, the piston comes back and displays out the used steam which has already lost its energy as work done. See, these are the components, don't worry. A steam turbine, same phenomena the steam is experiencing here. The boiler, you have learned a bit. The furnace, the fire seal, turns water into steam, means the boiling takes place. Somehow the steam comes, pass through this, turns the turbine, and condense this steam, energized steams finally becomes less energy and turn into water, water pump back. This water pump is pumped back to the boiler. So there is a cold water source in big coal power plants. You can see cooling towers for this cool water to be used in condensing this steam remain after driving this turbine or turning the turbine. So later we can learn more about this. Okay. So my question, you know that. Highly energized steam to produce mechanical work done. Steam engines, power stroke. Power stroke. Turbines. No power stroke. Steam engines. So I will take at the power stroke. Steam turbines. At the turbines. What happened to steam? What happened to steam? This is the turbine, this is the generator. Yes. Do you have answers? Even you can chat me. You can put into the chat. Or you can think about this. So piston moves. So it's the same. If this is steam, so what happens? Here, deliver a work. So this is work transfer from the system to the surrounding. Okay, still I'm waiting your answer. So work transfer, W. This is minus. So this is 1. 1. I'm waiting your answer. Put into the text at least. After delivering the steam, comes to 2. 1 to 2. So U2 is U plus W. So plus W is minus W now. Actually doing a negative means from the system to the surrounding. So this says that U2 is U1 minus W. See, E2 is E2 plus minus W. So E2 is E1 minus W for this one. So what happens? Energy level at U is lesser than energy level of 1. So very simple. So one observation is the steam losses energy. Of course, steam losses energy. So how steam loses energy? Two things taken place. Expands. Expands while moving the piston. Possibly piston against a knot. Yes. Expands while moving the piston against the knot. What expands? Steam expands. So this is the one. To work done for steam, steam should expand. What is steam? Energized. So high pressure, high temperature. Expands means moving towards low pressure, low temperature, low energy levels. So energized steam expands while moving the piston against a knot. So can this be the same? Of course. Steam losses energy. Expands. See, I will show you the expansion. Initially, steam sweeps here. Let's see. Anyway, it's very difficult to draw here. Yes. Initial steam is here. Then it, while turning, moves further. Then see, occupies a bigger volume. Further moving, occupies some more bigger volume. Increasing volume means expanding. Some more bigger volume. And once this is sweeping, another set of similar steam comes follow behind. Okay. So likewise. Comes here. Expansion. So energized steam expands. Okay. So here, while moving the mechanical component, that's also facilitating this expansion, moving the turbine against the load. Here the load is the load, the electrical load here at the generator. So this expansion is very important. So steam expands, energized steam. So expands, and what happens is steam become de-energized. So de-energized steam means energy released steam. So here, energized or energy loaded or energy laden steam. Okay. So energy released. Energized. So it definitely needs increasing of the volume. Also definitely needs this increasing of volume means the expansion taken place through this kind of mechanical component drive. Okay. Driving with the mechanical component. So two things. Expands while moving the turbine, the mechanical component. So that's the point. Okay. That's the point. See. Expands while moving or driving. The moving is okay. So this can be turning, or even can be turning, or maybe linear, pushing, like example in the piston cylinder arrangements. Okay, good. Then what can you say about pressure at one and pressure at inlet, let's say I, outlet O. So there is a pressure drop. How about temperature? Temperature drop. Okay. Pressure drops. Temperature drops. Internal energy drops also. Moisture, because some superheated, some energized steam, some steam turned into moisture. Possible. Okay. Pressure drops. Temperature drops. Internal energy drops. Means moisture. Let's say moisture doing this difficult work of turning turbine. They feel less energy. Cannot move. Cannot move means this low energy steam. What happens? Part of that turns into moisture, means liquefied, turns into liquid form. So some steam turn into moisture. Sorry, not to say moisture, liquid form. Possible. See, lost energy so much. Finally, that highest energy, low temperature, low pressure. Even no more steam 100%, maybe partially liquid, partially vapor. Some steam, so means a partial, okay? Some steam means partially. Turned into liquid means saturated vapor liquid. At low pressure and temperature. That's the point. I think in your smart device, you may be able to see this. When you am emailing this, So you know what practically happens. Then we can go for the analysis. Once you know what practically happens, then we can go for analysis. Because if without having any knowledge of this expansion, you are doing analysis, but you have no good technical know-how, okay? But now you can understand. Turn into liquid. So some steam, so partially turn into liquid form. In saturated vapour and liquid at low P and T possible. Okay, Bhutala. 329 now. 329. So you have another class at 3:30. So I have to stop now. So let me save your attendance. So I have already opened up a Google Classroom for you. I hope you all have registered for that. So later I will send you some important assignments, but today I will send you this this week weekly note also. So you look into this daily note, refer your text, also reflect your industrial experience and understand thermodynamics very well, because this subject is so valuable subject, and this is nothing to do with maths. Okay, so this is the knowledge depends on your understanding. That's all. So maths, language, nothing important, but try to understand that. The nature's phenomena, how we are adapting as thermodynamics. Okay, with this very good essence or the fundamental of knowledge, the rest, understanding your note and doing simple solution, not a big deal. Okay, so you know what importance as you are learning thermodynamics. Okay, see, so far I have not used any equation yet, you know, even today no equations. Yeah, so but very important. Not to say concepts, but nature's phenomena. So we try to make you understand. Thank you, Bhutala. It's 3:31, so let me stop the class. See you next week then. Okay. Bye then. Bye.
Thank you, sir.
Thank you very much, sir.
Thank you. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Bye. Bye.
Thank you.